about osmolarity and the movement of water. So this brings us again to review something we talked about many moons ago, osmosis. We know osmosis is the movement of water passively down its concentration gradient. So it's going to move from wherever there's lots of water to wherever there's a little bit of water. And that will be movement from the opposite solute concentration. So water is going to move from a low solute concentration, meaning that there's lots of water, to a high solute concentration, meaning that there's a little bit of water. And so water is reabsorbed following solute reabsorption. And this really ties into that concept that I was talking about earlier. We need to have the movement of solutes in order for water to follow. So water follows sodium, right? Water follows solutes. So if I'm reabsorbing solutes appropriately, I can reabsorb water appropriately. If I'm not reabsorbing solutes appropriately, then I'm not going to reabsorb water appropriately, okay? So the movement of solutes is vital to the movement of water. Okay. And so we can speak about the osmolarity of all of our body fluids as being about 300 milliosmoles. And to just describe what that means that there's about 300 milliosmoles of solutes that are dissolved in a liter of our plasma. And this is the osmolarity of our plasma as it relates to our other body fluids. And so there's typically no force for water movement in between our various fluid compartments. If we think about the ICF, which is inside of our cells, if we think about the ECF, which is including the plasma and the interstitial fluid, there typically isn't net movement of water in between those fluid compartments because the osmolarity of each of those fluid compartments is the same. And remember, we need a solute difference, a solute gradient in order to move water. And so if we don't have a solute gradient, then we have no osmotic force. We have no osmotic pull. We have no ability for water to move if we don't have the movement or the gradient of solutes. So typically we don't see the movement of water in between our fluid compartments. It pretty much stays the same. And so the kidneys come in and they compensate for changes in our osmolarity of our extracellular fluid by regulating what happens at the level of the kidneys. And to kind of make that a little bit simpler, if I am not intaking enough fluids, if I'm not bringing in enough water, then my plasma is going to start to be very concentrated. It's going to start to have more solutes than water. It's going to become really salty, we can think of it as. And my kidneys are going to step in to regulate that ECF balance. They are going to change the amount of water they reabsorb. They're going to reabsorb more water in order to dilute that salty plasma, okay? And so this is where the kidneys help to regulate our water balance of our extracellular fluid by changing how much water they reabsorb as a response to how much water you're intaking, okay? And an opposite example would be if I'm ingesting too much water. So if I'm ingesting too much water, my plasma becomes really dilute or really diluted. My kidneys are going to reabsorb less water in order to regulate that excess water in my plasma. And so I'm going to be losing more water through the urine and reabsorbing less water back into the plasma, back into the blood. And then finally here, water reabsorption is a passive process. So it's not active, it's based upon the concentration gradient, and it's based upon the osmotic gradient specifically. And to really kind of clarify this, if we think about the Starling forces, when we talked about Starling forces, we talked about this osmotic pull. So because these membranes are not permeable to certain solutes, they are only permeable to water. If I actively pump these solutes across the membrane, then I am creating an osmotic pull because the solutes are then going to pull water to them in a very similar way as the proteins would pull water to them when we talk about our Starling forces, okay? So water is not necessarily being pushed across this tubular structure, but it's being passively moved because of the osmotic gradients, because of the solutes that are at different concentrations. All right. Any questions on that before I go any further? So we're kind of running out of time here. So I'll see if there are any questions. Okay, nothing pops up. All right, so this is really a review, as I mentioned earlier. So the movement of water across the proximal tubule, we talked about this in our previous packet, and we said that most of the water, about 70% of the water that's filtered across the glomerulus is reabsorbed across the PCT, and this is unregulated. So this is happening irrespective of any external factors. This is freely flowing water that's moving from the tubule into the peritubular capillaries, and this is unregulated. In the distal tubules and collecting duct, most of the water is also reabsorbed, but this is regulated. And when we say regulated here, this is going to be influenced by things like ADH, which is antidiuretic hormone, as well as ANP. We're going to talk about ANP that's released from the heart that also has an influence on how much water is reabsorbed. And this really ties into what I was mentioning on the previous slide. ADH regulates the amount of water that's reabsorbed as a way to regulate our total blood volume. Again, if I'm ingesting a lot of water, I need to be losing a lot of water in the kidneys. And so I'm going to increase my water excretion through the kidneys by decreasing my water reabsorption. Alternatively, if I'm not ingesting enough water, if I'm in a dehydrated state, I am going to increase my water reabsorption, and I'm going to lose less of that water into the urine and move more of that water back into the capillaries under the influence of ADH. Okay. Alrighty, and so this is really the exact slide we had in that previous packet. We talked about how water is moved across the proximal tubule. Chloride transport happens passively across the basolateral membrane. Sodium transport happens actively across the basolateral membrane. This pumps all of these solutes into the peritubular capillaries, and so water simply follows by osmosis, right? Now we have more solutes in the plasma, less solutes in the tubule. Water can move from the tubule into the plasma according to that gradient. Okay. And here is just reiterating that idea, that concept, right? Sodium comes into the apical membrane passively. It's gonna also bring in glucose as a part of the secondary active transport. Sodium is gonna be pumped across the basolateral membrane actively. Remember, this is the sodium-potassium pump that's doing this. And then it's gonna move into the plasma, and that will facilitate more solutes here, less solutes here. So that's gonna mean more water here, less water here. And so water will simply move across these structures according to that water gradient or the solute gradient. You can think of it either way. Okay.